So as was mentioned, my name is Manolis Savva. I'm a faculty member at Simon Fraser University in Vancouver, Canada. And the title of my talk is Digital Twins for Embodied AI, Scaling, Acquisition, and Generation. And I'll begin first by trying to explain the title a bit. First, this beginning, the first part, Digital Twins for Embodied AI. What do I mean by that? I mean these high fidelity representations of real world scenes, indoor scenes like kitchens, living rooms that you see here on the left, that are useful for tasks such as visual navigation, but also manipulation, examples of which you see on the right. So these, high fidelity representations of the real world can have quite a number of uses for embodied AI and robotics. Now, for this second part, to explain what I mean by scaling, acquisition, and generation, I'll first describe a bottleneck that underlies the use of digital twins for embodied AI, which you've heard about actually from some of the earlier talks in the morning as well in this workshop. And that bottleneck has to do with the fact that these, digital twins don't come for free. In fact, they are quite expensive to acquire from the real world or to otherwise design. What you see here is a particular example of a reconstruction of a real-world house. This is from the Matterport 3D warehouse, Matterport 3D dataset, from which actually many of the examples that you saw in the previous slide came. And the green dots here are positions where a tripod was placed in this real-world house to scan and to acquire, the imagery that was needed to produce this high-fidelity reconstruction of the indoor space. As you might imagine, this process takes quite a while. So it's not that easy to scale real-world data acquisition. Now, an alternative to this is, of course, to rely on human-authored digital twins of 3D scenes. An example of which you see here from the Habitat Synthetic Scenes dataset from a couple of years ago. These have many advantages. They can be very richly annotated with ground truth information, all the semantics of objects that are present, other properties, examples of which you see here. But again, this is not something that comes for free. The process of designing these 3D scenes is highly laborious, takes a lot of time, and requires expertise. Here you see a video that's actually sped up many times relative to real time, showing what it takes for a person to author this scene, to create the interior space, even if the objects themselves are already available. So given this bottleneck of creating digital twins, what can we do, right? That's why this is an open challenge, and there's actually quite a bit of research in this direction. And really, this is the goal of this talk today, to talk a bit about the various ways in which we can try to alleviate the bottleneck of digital twin acquisition and generation. And the talk will take the form of a quick series of vignettes, overviews, light on detail, just to convey some of the key ideas of a few recent projects that you see displayed here. And I'll go through them, one by one. So beginning with this, project here on the top left, a project called Scene Motif Coder from last year. The idea here, the motivation, was to tackle the generation of 3D scenes compositionally, relying on a pre-existing data set of objects, and algorithmically assist people in putting together richly detailed scenes like the example that you see here. In other words, to populate an indoor space with much of the detail that exists, right, in our everyday environments. To have a table that has all this utensils, cutlery, bottles of wine, and so forth. And this is addressing a particular limitation of prior work on 3D scene generation, of which there's been quite a number of papers. And that limitation is that, it's focused primarily on large furniture items, objects such as tables, chairs, and so forth, and not really as much on smaller objects, and in particular objects that, convey this, rich detail of the real world. So scenes are unrealistically empty in much of the prior work. These, of course, this limitation is, of course, due to a number of challenges. The fact that such objects are rarely captured in scene data sets, The fact that these arrangements of small objects are highly compositional in nature and that they are in tight geometric contact. All of these make it challenging to generate arrangements of smaller objects. How did this project try to tackle this? It had a couple of key ideas. One was to learn from examples. Examples like the one that you see here, a stack of cement plates. A person maybe designed this and gave it to us and said, this is what a stack of plates looks like. If we can extract the basic spatial pattern or motif out of this, then we can perhaps hope to generalize to other types of objects of a similar arrangement, such as a stack of books. That's one side. And then the other side is that these so-called motifs or spatial arrangements can be well represented by code. So we might take a code synthesis approach to try to produce these motifs to make them into actual arrangements of objects. And so that's really what the whole framework here is, learning from a few examples of these so-called motifs, creating a library of meta programs of code that can be called with appropriate variables filled in and instantiated at inference time, given a particular description of now, a stack of 4 books, producing that arrangement. And of course, as you might imagine, this is all powered by large language models and vision and language models. And really the key advantage of doing it this way is that now we can put together some of these simple motifs to populate richly a particular 3D scene. The example I was showing earlier consists of a handful of these motifs used to populate that tabletop. Another advantage of this approach is that since we are using code to represent these motifs, this remains human readable and human editable. Here we can produce a derivative motif that has an extra object on top of a stack of plates. As follow-up work to this, from this year, we extended this strategy at the scale of entire rooms. Here you see an input description at the top, describing a dining room arrangement. And really the idea here is to decompose this long sentence into various spatial scales, starting from the scale of the whole room, laying out the dining table, in the space of the room, and then continuing on to other, smaller scale surfaces, such as the tabletop surface, to produce this, layout that you see on the right. This strategy of compositionally putting together 3D scenes from pre-existing objects is quite powerful. There's been quite a bit of work in recent years on this. And for more, on the body of work that, has been done in this area, I would suggest that folks check out this survey paper that tries to categorize what has happened over the past few years on compositional 3D scene generation. So that was really the first part. Now I'd like to return to the title and emphasize one part of it here, this for embodied AI for robotics, and say that there's a bit of a disconnect. And the disconnect is because everything that you've been seeing so far is completely frozen in place. Both these real-world reconstructed scenes, but also, these synthetic scenes. So we can't move objects around. We can't open or close doors or interact with, the cabinetry, open the fridge, and so forth. So really, this is, not ideal, right? Because for embodied AI and for robotics, interaction with the world is where it really gets tricky. As this infamous example from the DARPA Robotics Challenge from quite a number of years back aptly demonstrates. Now, an early attempt to try to alleviate this, to create interactive 3D environments from real-world spaces, did multiple scans over time to observe the same space with objects manipulated and changed. But as you might imagine, again, this is hard to scale. So this was limited in its scale, only 100 or so environments. What can we do, right? How can we better scale? Perhaps if we look back to synthetic data again, and this is where I transition to the second project called Artiverse, the motivation here is to recognize that we have increasing volumes of static 3D data, from data sets like the ones that you see here. Wouldn't it be nice if we could somehow, make all of these objects be interactive, make all of them, possible to use in simulation, in examples like the ones you see at the bottom. And that's really the goal of this particular project called Artiverse. It's a dataset work that will be presented actually in a few days at CVPR. And the focus here is to enlarge the scale, but also the diversity of objects that are available for interaction in simulation. The problem that is being tackled is, of course, that there are two families of prior work, works that have scale but low realism, and works that have high realism, high diversity, but small scale, right, of these, synthetic and interactive 3D objects. So Artiverse tries to combine the strengths of both worlds, provide more than 5,000 objects that are fully interactive with high diversity, but also importantly with physical properties such as metric scales, per part materials, masses, also functional dependencies between parts, articulation parameters, and so forth. And how is this done? The way that this was done in a scalable fashion was to have a human-in-the-loop pipeline with 4 stages. The first stage being segmentation of the parts of these objects into meaningful parts that can move. The second stage being completion of interiors such that these objects are usable, right? Having an interior to the microwave so that plates can go into it. The third stage, annotation of articulation parameters so that our parts can move. And then the fourth stage, specification of physical properties, such as masses, coefficients of friction, and so forth. And with this pipeline, what was done here was to target actually about a dozen or so pre-existing static 3D object datasets, use those assets, enhance them into dynamic, into interactive objects, and then end up with a fairly large data set of interactive objects that can be leveraged for simulation. And here you see some examples of this leveraging in simulation for training manipulation policies, and policies in particular that can operate a microwave using this functional dependency of buttons opening doors and so forth. Now, this is a nice strategy, but what if we don't even have the specific static 3D object that we care about? What do we do, let's say, if we want a bed that's attached to a wall, one of those beds that can fold up? Do we ask a person to model this whole thing? And how much effort would that be? That's where really we can turn to perhaps generative models that provide for us a much more efficient way to scale production of synthetic 3D assets. And that's the third part here of my presentation, focused on a couple of works from the last 2-3 years. And this work specifically looks at generation of articulated 3D objects. The first example here had as a motivation the need to have controllable generation of interactive 3D objects. And the way that this was done in this work was to use as input conditions abstract graphs. You can think of them as kinematic graphs. What you see on the left here, capturing the critical parts and their connectivity in the kinematic chain. And from that as an input, produce the complete geometry of the object as well as the parameters that allow it to articulate. And to do that, what was really useful was to have a convenient abstraction for the geometry of the shape, a high enough abstraction that can allow us to really represent broadly a number of articulated object categories. A key idea that underlies this work was to then use attention to appropriately establish connections between part geometry, connectivity, and motion. And as you might imagine, this is a denoising strategy where we take representation, a tensorial representation of the complete object and its articulation parameters, and train a neural architecture to iteratively denoise from a noisy version. I won't really go into the details. I'll very quickly, just in the interest of time, show some results. Here you see a number of input graph examples on the left, as well as the category of the object that is desired. And then to the right, you see 2 output examples. Each pair of columns shows the abstracted bounding box representation and the filled-in geometry for that object. And as you can see, these are some plausible, completed, objects, examples of ovens, refrigerators, storage units, and so forth that have the desired structure in terms of the number of parts and articulate. Another useful thing that we might want to do is to match a particular image input, right? We have an image of a particular object that we would like to have as an interactive 3D representation. It would be nice if we could go from that image to the object itself. And this is the focus actually of follow-up work from ICRA last year, this project called Singapore on image conditioned articulated object generation, which actually directly builds upon the paper that we just saw with a fairly simple extension. Here we're using an input image, features that we can compute for that input image, and then those features really drive directly across a tension layer that connects with the previous pipeline that I was showing. And in this way, we are conditioning on a particular image's input rather than this more abstract graph representation. And again, I'll skip the details. Happy to chat more offline about those. But there's some results here on synthetic objects from synthetic data sets, rendered images on the left in each triplet are the input, and then the two columns to the right show the output object. And a few more results here on internet images. These images here are from product catalogs on the internet, and it's just to show that we can generalize at least a little bit to these relatively clean images that one might find to produce as output a 3D object with the articulation parameters that can allow it to be used in simulation. So this is a pair of recent projects on generative models for articulated 3D objects. Now, it's a good strategy, right? That allows us to produce perhaps, these interactive 3D objects at scale. But can we acquire complete 3D objects from the real world, right? The downside of these approaches, one limitation that I kind of swept under the rug, is that we still rely to some degree on a database of synthetic objects from which these parts are retrieved and composed together into the complete object. All these drawers and such needed to be modeled ahead of time. What if we don't have the exact geometry of the drawer that we care about? And that's where perhaps we should really go back to the real world and try to take the acquisition strategy, the reconstruction strategy again. And this will be the last pair of works that I'll talk about in the bottom right here from the past year or so. The motivation for this pair of projects was to really rely on egocentric video as the input modality, with in mind the advantages of casually captured and egocentric video, the fact that it's fairly easy to scale, right? It's relatively easy to ask a person to record a video, and it's highly informative. It contains a lot of the useful signals for what these common interactions with objects look like. Common interactions like, using a faucet here to wash a spoon, or opening the refrigerator door, or again, turning on the water to wash our hands. So this input video data is quite useful. Wouldn't it be great if we could convert a video to a fully interactable digital twin representation of the object that was observed? So the first work here, ITACO from 3DV this year, a few months ago, focused on this particular task from an input RGBD video producing an interactable digital twin. And again, at a very high level, it's a two-stage pipeline that first has a coarse prediction stage, establishing correspondences between static points and dynamic points, and then refining the initial estimates of object geometry and articulation parameters, segmenting movable parts, and so forth. And again, very quickly, just some results. Synthetic data results here, very simple objects, desks, USB sticks, and so forth. But at the time, the state of the art was it was quite hard to get anything reasonable out of it. And with real data, even worse. So even simple objects like books or just a single drawer on a cabinet unit, extremely hard to get the complete geometry and reliable articulation parameters. In this follow-up work, we really focused on this, the challenge of this task, EgoFun 3D, and this was intended to set up a benchmark for the task of going from egocentric video to a completely functional 3D digital twin. And really recognizing that there's at least 4 challenging subtasks here: segmentation from 2D, reconstruction of the 3D geometry, estimation of the articulation parameters, and then some notion of the functionality of this object. So a key abstraction here was so-called function templates to represent how the object functions. A so-called receptor is a part that maybe the human interacts with, and the state change in that receptor may lead to a state change in another part, the effector. Here you see an example of a stove, here, a range where the person turns a knob and then the fire turns on. And with this abstraction, we can then talk about representing actually more than just geometric changes, but illumination changes, temperature changes, fluid flows, and so forth, with simple mappings like linear mappings, binary, and so forth. And with this, convenient abstraction, we can then target, your simulator of choice. It's something that's portable enough to produce interactive objects in Genesis, Isaac Sim, behavior, and so forth. So given this, the effort here was largely to acquire the data set of egocentric videos, annotated with 2D segmentations, 3D segmentations, and articulation parameters, these function template representations, and then lastly, putting everything together, a complete interactive object, and put this together as a benchmark and use it to really study how well the state of the art does. The quick summary is not so well. Here you see, pairs of ground truth and prediction, and you'll note that the prediction in general, we have a long way to go in terms of having high quality geometry and high quality functionality recovery. So that's pretty much it. This brings me to the end. This was a quick journey through some recent projects that target more scalable acquisition or generation of 3D digital twins and using them to create interactive scenes. A few quick takeaway messages. Simulation for embodied AI and robotics is increasingly popular, but the digital twins that are necessary, acquiring them is a key bottleneck. One path to scalability is more methods for controllable generation of interactive 3D objects and then composition of those objects into scenes. And one path to have higher diversity and fidelity is to rely on egocentric video data and casually captured video data and create physically grounded interactive 3D objects out of it. And there are many challenging problems that remain, much potential for future work. All of the work that I just talked about happened in the context of the very vibrant community of SFU's Visual Computing and Robotics team. If you're ever in town in Vancouver, definitely get in touch. Come visit beautiful SFU campus on Burnaby Mountain. Has a great view of downtown Vancouver, what you see there on the right. And I'll end with a big thank you to all of my collaborators and the students who, of course, did all the hard work. And I'm fortunate to be here presenting it to you. Thank you, everyone, and I'm happy to take any questions.